boa tarde a todos. Entonces, hoy en el seminario de tópicos tenemos un convidado de Argentina, de la ciudad de Córdoba, o Ezequiel Leiva, que es profesor en la Facultad de Ciências Quimicas de la Universidad Nacional de Córdoba. Él se hizo doctorado también en Argentina, después trabajó 2 o 3 años en Alemania, donde fez seu primeiro postdoctorado, después también tiene un postdoctorado en Estados Unidos, y luego volvió a Córdoba, y desde el año 99 más o menos que es profesor titular de la Facultad de Ciências Quimicas. Él se especializó en toda la parte de teoría, comenzó con la parte de dupla camada eléctrica y la parte de electrocatálisis, y hoy está haciendo una transformación para la parte de aplicar seus conhecimentos en el desenvolvimiento de materiales y el entendimiento de la reacción electroquímica en baterías de ion-Litio. Entonces, Ezequiel, pode comenzar.
Ok, muito obrigado. Muchas gracias. I'm going to share my screen now. Wait a minute. 1 second. I'm present. Okay, I'm already sharing my screen. So I changed, and you can tell me, please, Roberto, if the presentation is right.
Yeah, it's okay.
Muito obrigado. I want to thank you very much, Roberto, and the organizers of this course for this kind of invitation. And thank you for the kind introduction. And I want to dedicate this talk to my colleague Ernesto Gonzalez. We met with Ernesto every IC meeting, and we are going to miss him a lot in the next time. Exponential growth. Everybody listening about exponential growth, but in some cases, I wanted to show here the exponential growth of the annual lithium battery demand as a function of time in the last year. And this shows this is going to be a huge business. For instance, if we speak about the amount of battery which are produced now, this is the order of 300 gigawatt hours. This is about the capacity. And speaking about the amount is about 10 billion of units, or speaking about money, it's about $45 billion. This is 2020, and of course, this is increasing very fast. So the battery business is increasing very strongly and will increase much more in the next time with the electrical vehicles. To have an idea of this amount, 300 gigawatts hour, I must say that the electric daily energy demand in Argentina is about 350 gigawatt hour. If we load at the end of the year all the batteries that are produced in 1 year, we are able to keep the electricity of Argentina working for 1 day. Well, so there is no wonder that you know how over the world the lithium-ion batteries are distributed and how important they are. So there is no wonder that this 3 person got the Nobel Prize in 2019 for the invention of lithium battery. And it's very interesting to see the combination of knowledge which is necessary to make the battery. On one side, good enough is a physicist, Whittingham is a chemist, and Akira Yoshino is an engineer. So it's interesting that if we want to go to make advances, we must combine knowledge from different fields of. Concerning the future of the lithium-ion battery for transportation, I think that the battery for 160 kilometers is already there. The technology is there. This may be a small quantity, 160 kilometers of autonomy for a car, but I mean, this is enough for many uses. And if you look at the economical predictions, if you see how the price of the battery electric car is decreasing, and you see that the gasoline car is already steady, that you will see that in about 2026, the electric car is going to be lower or of the same as the gasoline car. That means that will be a strong change in the economy and a strong change in the paradigm. Concerning our interest in Argentina, I must recall this is a study that we made some time ago, and we found that Argentina is able to produce renewable energies every year, equivalent to an amount of 1 billion tons of hydrogen. And this is about of 1/4 of the world energy demand. That means that Argentina has the potential of producing energy, renewable energy for the world for 1 billion people. This is very important. But if you know that this renewable energy coming from the wind or from the sun is not stable. That it's when you have a sunny day you have electricity. Otherwise, you don't. So you have to store this energy. And the same happens with the wind energy that must be stored. So I mean that this is in our country is ideal for renewable energy, but we need to store this energy. The other motivation is, the lithium triangle. The lithium triangle is this region where you have 80% of the reserves in brines of lithium. This is a triangle which is shared by Bolivia, Chile, and Argentina. And this is a very important point. Some people say, okay, but you have lithium, but what about the other materials you need for the battery? Well, I must tell you that all the raw materials necessary for making the lithium-ion batteries are already in Latin America, all the raw materials. For instance, Cuba has the third reserves in the world for cobalt. Chile has huge reserves of copper. Brazil is gifted with many natural reserves. Nickel is the second reserve in the world. Aluminum is the fourth in the world. Phosphorus is the fifth in the world. Iron, the second in the world. Manganese, the third in the world. You have in Brazil a huge number of raw materials which are necessary for the batteries. Even Paraguay, for instance, Paraguay has the first lithium reserves in the world. So I mean that we have lithium and we have all the materials that are required for the battery, but okay, all or nothing more than we need is technology. And this is something we must seek for. Well, concerning our laboratories, the place where I'm working, this is Laboratorio de Energía Sustentable from the National University of Córdoba. And there are 3 faculties participating in this laboratory: the Facultad of Matemáticas, Astronomía y Física, the Facultad de Ciências Exactas, which is the engineering faculty, and our faculty, which is the Faculty of Chemical Sciences. And there we are 2 institutes which are working in this laboratory: the Institute of Physical Chemistry and the Institute of Physics. So these 2 institutes and these 3 faculties have put this effort and developed this laboratory. This is some part of some site of laboratory. Now it is much larger. And I always mention our collaboration with Aldo Vicentin of Jorge Thomas. They helped us a lot to put to work our laboratory because we have no experience on that, let's say 10 years ago. And this was very important. We are also collaborating with Gabriel Correa, Perelmutter from Catamarca, and I must always mention my colleague Barraco, which is the physical counterpart. Now in this laboratory we're about 40 people working. Half of these people are physicists, and the other half are chemists, and there are a few engineers working there. So we have been working this lithium-ion battery business. It's about 2,000. We have been working in this lithium battery problem since 2014, and we are making some experience on that. And as Roberto said, I come from the theoretical field, so I cannot. I always put emphasis. We do experimental work, but I always try to model different aspects of the lithium-ion batteries. Well, there are many scales. As you know, the lithium-ion battery problem has several scales from a car, from the size of a car, going down to the atomic scale. And there are a huge number of problems that must be understood using different. And concerning this approach, this is something I'm going to speak today about, are simulations, computer simulations. And these computer simulations goes around different time scales and different length scales. That go from quantum mechanics, go through molecular dynamics, Monte Carlo, mesoscale, continuum modeling. When I say continuum modeling, I am speaking about partial differential equations, and finally engineering design, which is a higher scale. Today I'm going to speak about quantum mechanics, molecular dynamics, kinetic Monte Carlo, and this continuum model, different applications of this model to the problem of lithium. Before I want to say a few words on the lithium battery. As you know, the battery is made of a cathode and anode. And in the case of lithium-ion battery, you have lithium, which is moving from a cathode to an anode. Upon charging, You have the lithium is coming out to the cathode, is being stored in the anode. And upon discharge, what you use is the energy that you have stored. And in this case, the lithium ions move from the anode to the cathode. And the same happens with the electron, which are moving to compensate the charging that you inserted in the cathode. So this is called rocking chair battery. You have a lot of freedom to choose the anodic and cathodic material. That's why there is so much research in the lithium-ion batteries. When you look at this, you may think that the lithium battery business is a matter of bulk material. But however, when you look in detail, you will see that there are a number of interfaces which are involved in this problem. It's not only a problem of bulky material, but interfaces problem are very interesting and must be considered in the modeling of this system. Well, let's start with quantum mechanics. Quantum mechanics is the most precise calculation method. I want to address something which I find very interesting. And the point is that you can calculate from first principle electropotential. How does it come out? Well, it's actually very simple. If you consider an electrochemical system, and let's say you use a reference made of lithium bulk material, and you take here the material you have under considerations, if this system is in equilibrium, the free energy chain that you have to transfer an ion from, let's say, graphite into a lithium bulk, the free energy chain is zero as long as you are in equilibrium conditions. So, but you can decompose this transfer of an ion here through a number of steps. You can, for instance, take an atom out of the electrode, take it out here. To move it further, you can take an electron away from this atom and put it in the same electrode. You can bring later these ions to the other in the front of the other electrode. You can put it the same. Finally, at the end of this cycle, you are actually making the transfer of an ion from here to here. That is, the free energy chain, which is zero, must be equal to the addition of all the other steps. 1, 2, 3, 4, 5, 6, 7. The point is, if you take a closer look, some of these free energy changes compensate. For instance, this free energy 2 is compensated by this 6, so you can put them away. This free energy 3, which corresponds to putting an electron back in the electrode, is equally to the free energy chain 5. This is but changing the sign. So a number so these 4 terms go away, and finally you are left with 2 terms or 3 terms. One is the chemical potential of lithium in graphite, in this case, the chemical potential of lithium into the bulk, and the potential difference between these 2 electrodes. If you don't get the potential, you can see that the potential difference of this cell is nothing but the difference of 2 chemical potentials. So you can get that means that if you take the chemical potential, in this case of lithium in graphite, and you add the chemical potential of lithium in the bulk and divide by electron charge, you can get the potential of the cell. That's why you can, in this case, calculate. That means that you can very, very easily calculate the electron potential by ab initio calculation. What you have to do is to make one calculation for the insertion of a lithium atom in the material you have under study, in this case graphite, and you have to insert a lithium atom in the bulk material, and from this you can get the theoretical potential difference of the cell. This works pretty good. And if you are interested on that, you can take a look. I always advise to take a look in this page. This is the material project, which was headed by Gerber and Seder, and they made a lot of calculation for many materials. So you can, if you are interested in a given material, you can go there and look inside, and you will find the electron potential which is predicted for this material. Otherwise, if it's not there, you can of course make your DFT calculation, as we will do, and calculate the theoretical insertion potential of lithium in a given material. Well, the methodology we use to do that is the density functional theory, which is due to Walter Kohn, who got the Nobel Prize in 1998 for his development of DFT. And there are a number of programs that can make the calculation for you. Well, in our case, I will give some examples how we estimated the insertion potential of lithium into a reduced graphite anode. Reduced graphite anode is a graphite which has been modified by some oxidized species and further a bit reduced. So you can use then you can now then estimate or consider different structure and analyze which is the insertion potential in lithium in this structure. You can predict the electron potential you expect to have with this system. These are some details of the DFT calculation we developed with the quantum espresso package. And here we have some results. So, I mean, you can, as I told you, there are two things which are interesting to consider. One is the binding energy that tells you how strong is lithium, which is how strong is the interaction of lithium with this type of structure. And you have to calculate the energy of the whole system. And you have to subtract the energy of the substrate and the energy of lithium. And you get an idea of the binding energy. On the other side, you can calculate the lithium potential when you have also to conceal the energy of the lithium system to subtract the energy of the reduced graphite. And if you subtract the energy of the bulk, potential insertion potential of lithium in this material refer to lithium bulk. And this is, for example, this is the energy value you have to insert, for instance, lithium in this close to an oxidized species in this reduced graphite oxide. You get the binding energy which is relatively large as compared with the binding energy that you have to insert a lithium ion in graphite, in a graphitic zone. No? Because I want to stress, this is graphite with some oxidized species. Here on the right, you are inserting lithium in a place without far from oxygen, and here you are inserting lithium in a place which is close to some oxidized species. You can see that the binding energy is much larger, lithium is close to some OH species, and the lithium potential is accordingly larger. That means that you put lithium in this material, this lithium is going to be inserted in this material at the potential which is considerably higher than if you insert lithium in a place which is far away from OH. So what you can do is now to try to simulate the energetics of a galvanostatic curve. And you can, in this case, we have taken two layers of oxidized graphite, and we have inserted in a sequence the ions in 1, 2, 3, 4. We have always looked for the lowest energy conditions, and we have inserted different number of ions column with this sequence. And this is another approach where we have inserted all the ions in the same layer, and afterward we have inserted all the ions in the other layer. This gives you an idea of how it's going to be the energy distribution and the potential, the insertion potential as a function of the capacity. And you can see that when you have a small number of ions inserted, the insertion potential is relatively high. But as you put more and more lithium inside this material, the energy decreases, and finally you come very close to the lithium bulk deposition potential, which is here the zero. The potential it refers here to bulk lithium ion. And this is to show you the galvanostatic curve, where you see how the potential changes as a function of the specific capacity. And you can see that at least from a qualitative aspect, the curve of potential as a function of capacity is similar to this curve of the potential as a function of the specific capacity. That means that when you start to put more and more lithium inside the material, you get a potential which is very close to the lithium the lithium bulk deposition potential. But for a small number of ions that you are introduced, the potential is about 1 volt over the reversible potential for lithium deposition. Another thing that you can understand or you can study is the exfoliation energy. You can see how difficult it is to split or to take away one layer from the other, and this gives you an idea of how stable it's going to be your material. And you can calculate the exfoliation energy in joules per square meter. This was for bleaching graphite. This is for reduced graphite oxide, and this is for graphite oxide. You will find that you see that in the case of graphite oxide, the interaction energy between layers is considered stronger than graphite. But the important thing is that as you lithiate, the interaction between the layers becomes stronger. That means there is no, you shouldn't be afraid of losing your material. I just lithiate this material, but you see that the interaction between layers increases as you put more lithium inside. Well, you can also play around with lithiation defect. This is, for instance, the binding energy of a lithium atom in this defect. And you can see that this is the position potential. And you can see that if you have defective graphene surface, you expect also to have a position potential which is higher than the position potential of lithium. Well, this is some of the conclusion that concerning the system. If you lithiate the structure, you have a higher adhesive energy. That the absorption mechanism and binding, it depends of lithium is absorbed in proximity of oxidase group or not. We can also conclude that lithiation potential of the reduced graphite oxide are higher than those of pristine materials. And also it's interesting to see that the lithiation potential you get are within the range of the values that are observed experimentally. Well, there are other, we did other applications that can be done with DFT, with the first principle calculation, is to study lithium sulfur batteries. Lithium sulfur batteries are similar or are relatives of the lithium-ion battery, where you have a nano which is made of bulk lithium electrode, and you have a cathode where you have a material where you load sulfur into carbonaceous species. As you start to lithiate the structure, sulfur goes through different species, which are polysulfide, and finally you end up with lithium sulfide. The problem is that these intermediate species between sulfur and lithium sulfide are these polysulfides, and these polysulfides dissolve into the solution. They eventually migrate to the other electrode and react with lithium. So you get a number of andesite reductions, which are and this process of motion of these polysulfides to the anode are called polysulfide shuttle, and this decreases the capacity of the battery, and these are andesite reactions. Well, you may ask why people are interested in lithium sulfur battery instead of lithium-ion battery, which has to do with the specific capacity. Here you can see from the blue curve, this is the specific capacity per unit mass, and you can see that the capacity of lithium sulfur battery, which are denominated post-lithium technology, is considerably larger than the capacity of the lithium-ion battery. This is one of the reasons that people are trying to switch. That if these batteries are still not ready, there are many improvements to be made before they can work. This is one of the problems that polysulfide shuttle. But these batteries are very promising from the viewpoint of the storage capacity. Now, how can this problem be solved? The problem of this polysulfide shuttle, one is to put separators here, to put something here that separates the cathode from the anode and trying to prevent the migration of polysulfides. Another approach is to put, instead of putting the separator, to put some material here which is able to retain polysulfides. So one of the things this make a trap for polysulfide. You can put a trap here, or you can put a trap here. The difference is that in case you put something here, that the material you're putting here may also have a catalytic effect. That is something which are considered also by DFT calculations now. Well, one of the things that we investigated with this is Guillermina, Luque, and Patricio. We investigated the capacity of some modified graphene surfaces, modified by substituting them with atoms. We doped this surface with heteroatoms, and we analyzed the interaction of polysulfide with these heteroatoms. So we took a typical polysulfide. This is a 6-atom sulfur change, and we consider the interaction of this molecule with these surfaces, doped or non-doped with these heteroatoms. We took as a reference system, we took pristine graphene. That is, we put this polysulfide interacting with the surface, and we calculated the energy. If you put a polysulfide molecule interacting with the surface, you get an energy of minus 0.2, which perhaps doesn't tell much to you, but it's easy to estimate the time that a polysulfide would remain on the surface dependent on this energy. You can make an estimation of the time that the polysulfide will remain on the surface by using transition state theory. Transition state theory tells you that the rate, that is the reciprocal of the time, is a prefactor, a frequency factor, multiplied by the activation energy that you must take to take this polysulfide away from the surface. If you use transition state theory to make an estimation, you will find that if you have an interaction energy of minus 0.2, the time that this polysulfide should be remain trapped on the surface is about 0.3 nanoseconds. That means that this number is very small. It's too small to retain the polysulfide for a long time. Well, we use different, we consider different surfaces, substitute with boron, with oxygen, nitrogen, fluorine, and the vacancy. We study different systems and we calculate the energies, and from this energy you can make an estimation of the time. Well, here you have some estimation of the time depending on the energy. For instance, with an absorption energy of 0.44, you can get a residence time or retention time of 4 microseconds, which is very small. And you can see for none of these systems, you get a reasonable trapping time of the polysulfide surface. Well, we consider many type of atoms: boron, carbon, nitrogen, oxygen, fluorine, aluminum, silicon, phosphorus, sulfur, and chloride, and we found that the only good candidate for this is aluminum. So, and you can, of course, you have here the energy as a function of the atomic number, or you can plate also the logarithm of the retention time as a function of the atomic number. And as I told you, you can see that the only case where you have a reasonable, I mean, when I say reasonable, is more than one day or more of retention time of this polysulfide surface in the case of aluminum. We also consider, we have also considered another type of surface, like oxidized graphite surfaces. I don't have the time to speak on that now. But we can conclude that if you talk graphene with different heteroatoms, you have a limited ability to retain polysulfides. Only aluminum seems to give satisfactory result. This is something I did not discuss here. If you use a reduced graphite you try to use reduced graphite to keep the polysulfide, you have the problem that your polysulfides react with the surface, and at the end of the day, you finish without oxygen on the surface because a polysulfide is going to take that away. This is something that we studied. I'm not going to speak on that now. And okay, this is something which must be further investigated, the possibility of retention of polysulfide by oxidized graphite surface. We got one step up in the computer simulation of different systems, and we go to molecular dynamics, another tool to investigate processing lithium-ion batteries. Well, if you probably read that silicon anodes are very promising for anodes for lithium-ion batteries. If you look at voltage and capacity in this scale, you will see that graphite is here 370 something milliamp per gram, which is relatively small. But you look in different materials, you will find that silicon has a very high anode capacity. That's why silicon was considered as a much better candidate than graphite. Graphite is the material that you have in your handies now. This is the anode, the typical anode material of commercial batteries, but you can see silicon is very promising. Why? Well, silicon has the highest capacity of all known anode materials, and also silicon is abundant. There is a lot of silicon on Earth. This is the second most abundant element on Earth. But silicon has problem. One of the problems is that when you lithiate silicon increases 300 to 400% its volume, and when you take lithium away, you get these cracks. You get the mechanical state, you get material fracture, you lose a lot of lithium because these cracks down and you lose contact of the silicon in the anode. So there are a number of problems with silicon that need to be addressed. And for this reason, we decided to simulate by molecular dynamics the insertion of lithium in silicon anodes. This is a typical curve for charging. This is a voltage as a function of capacity. This is a galvanostatic charging. You get this curve. And this is hysteresis. You have a strong change in the curve. This is not good for the battery. And this is that same things that happen here. And one of the things that's happened that people know that if you look into X-ray diffraction, you will see that, and you calculate the ordering of the surface, which is reflected in the radial distribution function as a function of the distance. You can see, for instance, in pristine crystalline silicon, you get a number of peaks that shows that your structure is very ordered. But if you charge and discharge your material a number of times, you will see that this very nice structure disappears. That means that your material is becoming amorphous. And so we decided to study this amorphization by molecular dynamics. Molecular dynamics is very simple. It's a very simple thing you can do with the computer. You just solve the Newton's equation. You solve numerically the Newton's equation. That is the force, is the mass by the acceleration. And what you have to need, you need the forces to integrate this equation. And the forces you get minus the gradient of some potential energy. And this potential energy must come from some reasonable assumption. And in this case, we took a reactive potential. The reactive potential is something which is not quantum mechanical, but gives you an idea of the interaction between the particles of the system. The problem is that when you start to move the system, you have very, very high energy barriers. So you have very, very high energy barriers. That means that this is going to take a lot of time for you to make the simulations. I mean, and there is no way to go around if you have energy of the order of 1 electron volt. The silicon bond is about 2 eVs. That means you have a huge barrier to overcome, and this is not possible by ordinary molecular dynamics. What we did is use an accelerated dynamics, which is a version of molecular dynamics that modifies the energy, the free energy, or the energy landscape, allowing that you move the atoms much faster than with ordinary molecular dynamics. This is the PhD work of Francisco Fernandez, and this is collaboration work with Alexis Paz, who is a specialist in accelerated molecular dynamics, and Manuel Otero. So if you modify that, means if you look at the original shape of this material, this may look like this, with huge energy barriers that you will not be able to overcome just by integration. But if you modify this energy landscape, you will move the system much faster. As an example, I show you on the left. On the left, you see an ordinary molecular dynamics. That is, you solve the Newton equations for these systems, and you can see that, okay, you can see some evolution, but when you make an accelerated molecular dynamics, you see an evolution, and a very, very different evolution of the system. And you can see that on the right, that you get some change which are formed. And there is no way that you would be able to get that change by the simulation on the left. That is that by making this accelerated molecular dynamics, you can get this structure that by no means you would be able to get by ordinary molecular dynamics. This is the procedure we use to get these structures. And one of the things we checked is we wanted to see if we get the volume change when you lithiate this structure as a function of X, where X is the number of lithium atoms with respect to silicon. You can see here these are experimental. The circle, the blue line, are experimental results. The black line are DFT calculation, and the red line are the computer simulation we did with this reactive force potential. That means that we are getting at least a relatively good qualitative trend for the increase of the volume of the alloy as a function of the lithiation. The other thing that you can get is also the pair distribution function. The pair distribution function is some sort of normalized local density, where you can see that how your atoms are distributed in the neighborhood of another atom. This is the lithium-lithium distribution. This tells you how lithium atoms are distributed relative to a central lithium atom. This is the silicon-lithium distribution function that tells you how the lithium atoms are distributed around silicon atoms, and this is the silicon-silicon distribution function. One of the interesting things we found here, and this is something we are concentrated in our study, that you get the splitting of the second nearest neighbor. Another thing that you can investigate is the coordination number to first and second neighbors, and you can get, for instance, the coordination number of lithium with respect to lithium, which is this line, and you can, as a function of the lithiation quantity of the lithiation, you can see that if you put more and more lithium atoms on the system, your number of nearest neighbor comes from, let's say, 2 to practically 12, which is very close to a close packing structure. The novelty here is when you look into silicon. When you look into the silicon neighbor of silicon, you will see that you start with 4 neighbors, which is something expected for the tetrahedral geometry of silicon. But if you put more and more lithium, you will see that your number of neighbors of silicon decrease, but comes close to 2. And this is correlated with the formation of chains that we have seen before. This is an evidence for the formation of chains. But even if you don't look into the movie, you can notice that you have a number of neighbors which is close to 2. You can look also in the second number of neighbors, and you can see here that the second number of neighbors increase from let's say from 5 to about 35, or of the order of 40. You have a very, very important number of second neighbors in this system. Well, this is something we are considering now, and this is what to show you that we have. These are very, very brand new results. So we have put to work a reactive field where we can study the formation of lithium amorphous silicon lithium alloys. We have reproduced the volume expansion, and the distribution function has shown some interest characteristics which are investigated now to know the consequence for some techniques. The next technique that we'll address is kinetic Monte Carlo simulations. Kinetic Monte Carlo simulations is another tool. Graphite is a system. We'll go deeper into the battery, but I mean it's the same as before. You have an anode which is made of graphite, and lithium is inserted in this graphite layer. And when you look in the voltammetric behavior, you will find that lithium has a number of processes where lithium is inserted in this material. These processes that you can find in the voltammogram are related to some stages. And these stages are different layers, lithium layers, which are separated from other lithium layers into graphite by a number of empty layers. So as intercalation proceeds, you get layers which are coming closer. As they intercalate, this comes in this sequence. So this was an interesting system to simulate. We constructed a graphite lattice. The first thing we use here, this is not molecular dynamics, we use a lattice system. And you have to use the Hamiltonian to describe the interaction between the particles of the system. This Hamiltonian contains terms which are relative to the interaction between the lithium ions, as I show here. And you have also interaction terms between lithium atoms which are a different layer, and these are repulsed. So you have a part of this potential which is attractive, which are due to the interaction of lithium ion in the same layer, and you have a repulsive contribution with this interaction between lithium ion in different layers. So you have to, once you have a Hamiltonian and you have a lattice, you can calculate. But there are different ways to calculate. One is to use some mathematical tools coming from statistical mechanics, where you have to evaluate the so-called partition function, which is the sum of all possible energy values of the system. And from this partition function, you can calculate the probability of finding a structure, and with this probability, you can calculate any property of the system. This is one way by statistical mechanics. The other way is by Monte Carlo simulation. Monte Carlo simulations are just a way of generating different structure, and from this different structure, you generate average, and this structure that you generate a representative of equilibrium, you also can calculate now the average properties, but not for statistical mechanics, but just running a number of configuration of the system. This is in some sense similar to molecular dynamics in the sense that you get configurations, and from this configuration you get properties, but it is different in the sense that there are equilibrium properties. You have no dynamic information in this Monte Carlo simulation. Well, you have to make some moves. The moves involve the creation and destruction of particles in the system, and this is a Monte Carlo simulation where you can see first the formation of stage 2 and later the formation of stage 1. So we can get, and you can, from this information, you can see how lithium becomes inserted in graphite. You can calculate voltammograms, for instance, equilibrium voltammogram. But more important is that you can get from this simulation the entropy of the system. The entropy of the system can be measured, this has been measured in the literature. You can change the temperature. From the change of the temperature of the system, you get different equilibrium potential. If you plot the equilibrium potential as a function of the temperature and you take the derivative, you can get the partial molar entropy. And when you plot the partial molar entropy as a function of the configuration of the system, you find this behavior. You see coming down of the partial molar entropy, you see a step at about 1/2 of the filling of the structure, and you'll later see again a decrease. Well, the point is that we have simulated with the previous model the partial molar entropy, and we get a good agreement with this experiment. These red are simulated data, the black ones are experimental data, and they show that the model is able to reproduce the behavior of this system. Which is the origin of this step in the partial molar entropy? Well, it has to do that we have, when you finish to fill an ordered structure and you start to fill a disordered structure, you get a step in the partial molar entropy. So we investigated this by more, I will not stop on this, but you can, the same thing we did with simulation, you can do with simple model. You can take a model with, instead of having one energy state, you have 2 energy states. And from this model, you can calculate from statistical mechanics the properties. This is, you know that the entropy is proportional to the degeneracy of the system. If you have if you put a lattice gas on a model with you put n particles on n side, you will see that the entropy goes to the maximum, because when you fill the 1/2 of the side, you have the maximum entropy. As you take the derivative of this curve, you have this partial molar entropy behavior, which looks something like experiment, but you don't have a step like this here. If you consider the addition of 2 systems, that is the filling of 2 lattice, you expect something like this. This is for very rough stated, but you fill 1 layer and you fill another layer, and you would expect to find a huge step. Of course, you can take the previous simple model and you can calculate the property by ordinary statistical mechanics, where you can calculate the free energy, the entropy, or the chemical potential for the partition function. That is the old-fashioned statistical mechanic way, and you can get the entropy as a function of the configuration. And you can see that if you have, instead of having one single lattice, you have this maximum entropy at 1/2. If you have this system, you have the minimum in the entropy in this way. Why? Because you start filling this layer here, and finally, when you go on filling this layer, at some point the entropy decreases because you have no more configuration to find. But as long as you start to fill the other lattice here, you get an increase again in the entropy. This is about a very simple model that we use to understand what the complicated computer simulation show. And this is the result of the statistical mechanical model, where you see that this step in the partial molar entropy can be understood in much simpler way. Well, this is and I want to discuss. I think that I'm running out of time, but the other thing that you can consider, and this is the PhD work Maximiliano Gavilán in collaboration with Oscar Oviedo, Alejandro Pinto, and Beatriz Lopez, and it was to put the time. And to put the time, you can no longer do Monte Carlo, ordinary Monte Carlo. You have to use kinetic Monte Carlo. And kinetic Monte Carlo is a method where you put time into question. And the idea of kinetic Monte Carlo is very simple. You have to have a number of states and transition. You have an initial state, you have different final state, and you calculate the probability of this the rate of this transition to the different states. And from this rate, you just throw a number, a random number, and you choose a process to happen, and so you go on with the simulation. The nice thing that when you use this kinetic Monte Carlo simulation, you can introduce realistic things that the insertion. You remember that when you spoke about ordinary Monte Carlo, we have insertion but everywhere in the system, but in realistic systems, you don't have insertion everywhere. You have only insertion at the interface, like here. And you have, of course, diffusion of the ions. So in realistic systems, you have to consider, in a kinetic system, you have to consider the migration of the diffusion of ions inside the layer, and the exchange, the ion exchange at the interface. You can now write a number of rate equations, consider the energy, the free energy, the activation free energy from this, and you have to set up mainly two barriers. One barrier for the ion diffusion of ion inside the material, another barrier for the exchange of ion on the surface. So with this model, you can go on, and you can see here how you are inserting ion from the left. Ions are not coming from everywhere like in ordinary Monte Carlo, but you are putting really the physics. So we're putting the exchange, the ion exchange in this side. And well, if you compare, and this is, again, this is simulation where you let time advance, and you find the feeling of, here would be the feeling of one half the layer. If you compare the kinetic simulation with the ordinary Monte Carlo simulation, you will find you get a number of defects. And these defects have been addressed a long time ago in the literature. There are two models to describe the feeling of a lattice, of a graphite lattice with ions. One is the Rudolph model, which shows a very ordered system, and the other are the Daumas-Herold model, which shows the number of defects. So we were able, we start consider this system, and we could find out which is the origin of this defective structure. The origin of this defective structure is that when you start filling ions into the system, you get a homogeneous distribution. At some point, your system should go to this stage where you have one filled, one empty, one filled, one empty. But the system is not able to do that, because in order to do that, you should take away all the atoms and put them inside again. So this defective structure the origin of this defective structure is a kinetic reason. The kinetic reason is that the system cannot reach a proper equilibrium and try to do the best it can. They discussed this we published a work on that. We were surprised because at the beginning we thought the results were wrong, and actually what we're finding is a very, very interesting kinetic phenomenon. From this kinetic Monte Carlo simulation, you can also make cyclic voltammetry, or you can get other techniques. This is, for instance, cyclic voltammetry. You can run cyclic voltammeters at different rates, and you can study, depending on the rate, the hysteresis in the isotherm. You can very, very nicely study kinetics effect by this kinetic Monte Carlo simulations. You can also make chronoperimetry, and there we developed a number of simulations where you can study, you can simulate potential step, and with this potential step, you can study the transition between the same stage or between different stages. And this is, experimental find that the representation of the current as a function of time is one maximum and two maximum, depending on the transition between different stages, as you can see here. And of course, we made the simulations, and we found the upper are experimental curve, the down are kinetic Monte Carlo simulation, and we found results which were very close to experimental results. This is, for instance, this is a step from, for instance, from E3 to E5. That is from phase 2 to phase 1 of graphite, and this is the simulation. Wait a minute, I don't know if the simulation runs. Well, I don't know why the simulation is not running now. But when you simulated the current as a function of time profile, we found one maximum, one or two maxima depending on the conditions. And the reason of this maxima, why there is the simulation is running now, I don't know why. Oh, sorry. I want to go. Let me go 1 second. I think it's not working. Just 1 second. I try once more. Here. Well, here you can see what happens when you start feeling this. When you run from this structure for the other structure, you get a feeling here, and you take a closer look into the detail of the way you feel. You will find that you get here the occurrence. This maximum has to do with the clock. You have the clock here, and this clock is responsible for this maximum here. We get exactly the same information at the experiment, but people making the experiment, of course, they cannot see what's going on with the system, at least not with the technique they have. And we could find that the reason, the origin of these maximums has to do with this clock, which is from here. You can also, of course, make, instead of intercalation, you can write the intercalation, you can empty. You make a step, a potential step in the opposite direction. You can also see how your system gets empty. And you can also simulate the curves. But the interesting point is that when you intercalate to run from one structure of the other, in the case of intercalation, it takes to you 40 seconds, but the same process, but the reverse process takes 9 seconds. That means there are huge difference between intercalation and the intercalation, and this has to do with the formation of clocks at the end of the electrode when you make the intercalation. I don't have time to discuss on that, but you can also get diffusion coefficients as a function of the occupation of the system, and you can also calculate exchange current density for this system by using the same procedure. What you have to do to make the exchange current density is to count the number of ions that come in or come out from the system, and that way you can calculate the exchange current density. And finally, and I think I'm running out of time, but I will briefly mention what we call continuum modeling. Continuum modeling has to do with the solution of partial differential equations, and our work was motivated by this work of Unwin and co-workers. I remember as I was in South Africa, I saw this interesting talk. They can study by electrochemical cell scanning microscopy. They can study the behavior of single particles on the system, and they can study the lithiation of lithium manganese particles. And they found that depending on the type of the particle, they get different behavior. So we decided to simulate the system by resolving the partial differential equation coming from the system. These are experimental voltammograms, and you can see the voltammograms are reversible at low zero fluid rate, and they change to be reversible by higher sweep rate. There is some thermodynamic model for this system. Some people have modeled the thermodynamics, not the kinetic, but thermodynamics, and we use the thermodynamic information to produce a more developed model. Again, Maximiliano made the calculations. So we fitted the voltammetric behavior at very, very low sweep rates. And from this information, we could develop a model to consider several sweep rates. So what we did is to solve for this system. We solved the fixed diffusion equations inside the material, coupled with the Bartle-Former equation on the surface of the material. And we did this for different geometries. And we constructed voltammograms. What you can do here, you can see with the voltammeter, you can sweep, you sweep the potential, you get the voltammeter, and you can follow the evolution of the concentration as a function of time. And from this, we constructed, we did for a finite system, and in the case of finite system, you get two parameters which represent the behavior of the system concerning reversibility. On one side, there is one parameter that contains the heterogeneous rate constant, and there is another parameter that contains mainly the diffusion length of the system. So what people do usually is to make a diagram of phases of reversibility, where depending on the rate constant, you get a larger, or I say, depending on the relationship between the rate constant and the sweep rate, you get reversible or irreversible behavior of the system. And concerning the size of the system, you know you get a behavior which is called semi-infinite diffusion or surface wave. So we made this phase diagram for this system, and this diagram are useful. For instance, here on the right, you can see that in this system you can rate the behavior of this reversible or irreversible depending on the sweep rate, and you can rate the system as infinite or semi-infinite depending on the size of the system. And this is useful because what you can do is, for this compound, you can look which is your sweep rate and which is the size of the system. And if you are here, if you are at a certain point as you are here, you are going to know with this diagram, you can know if your system is going to behave reversible or irreversible, or it's going to have a behavior like those of infinite diffusion or something which is running only on the surface of the system. And finally, what was interesting to see for this system, that depending on the type of diffusion, you get different type of voltammograms. If you have spherical diffusion, you expect to have a voltammogram like this, which runs relatively rapidly to. These are simulations. If you have a spherical diffusion, you have a voltammogram with this peak runs very rapidly to zero. On the other case, you have planar diffusion. You have a drop of the current which is much slower. Well, I think that this type of behavior explains the different type of behavior that was found in the experimental cases that I have shown before. So we have a phase diagram that can tell you how is your system going to behave concerning reversibility and concerning the diffusion, the type of diffusion it's going to have. And finally, a few words on modeling. What happens concerning the future models battery? The number of papers that is appearing on lithium-ion battery is also increasing exponentially. In the case of like the various, I say this is a recent work I wrote on the thing, and the future seems to be have to do much with multi-scale simulation. Multi-scale simulation are simulations that use the different fields were analyzed today, but they put them together and they use as feedback. They use one model to run to the other and run to the other, and they go back again, improving the quality of the model. This is something we have not done yet, but seems to be the future. If somebody wants to read more on multi-scale simulation, I advise this nice work of Alejandro Franco and co-workers. So I want to thank Roberto and the organizer of the invitation, our Ministry of Science and Technology, CONICET, our Secretary of the University, or many people who have helped me on this, Danilo Barraco, Aldo Vicentin, Jorge Thomas, Ernesto Carlos, who awakened me the interest for lithium batteries, Juan Colés, who was here, the EY Tech, which is an enterprise that we are working in collaboration in the experimental part. And this is part of the staff. This is the people. This is part of the people working in the laboratory of Energías Sustentables. These are more of the people, and this is the place where I work in the Faculty of Chemical Science. So, and I thank you again for your kind invitation. I hope you are still there so I can ask any question that come out.
Okay. Muito obrigado, Ezequiel, por la palestra, es muy interesante. Tengo varias preguntas para hacer, mas obviamente primero tenho las preguntas. Tenho uma pergunta, se você pode abrir, Ezequiel,
la charla,
el chat.
Ah, el chat.
Tem uma pergunta, você pode ler e responder. ¿Você entiende? Si sí, no, paso la traducción.
¿Te gustaría saber sobre la aplicación de esa tecnología? ¿Cuál tiempo se usa en la batería? ¿Cómo se descarte de periodos, selección de componentes, viable, vista técnica, económica, etc.? Bueno, las baterías tienen, la duración de las baterías de litio son justamente sumamente nobles, y ustedes ya lo saben por la tecnología que hay. Las baterías usuales aguantan miles de ciclos y hay algunos materiales como los titanatos de litio, materiales anódicos y el óxido de litio manganeso, o sea, depende de los materiales, pero los materiales más nobles van a durar decenas de miles de ciclos. La batería que tiene titanato de litio como ánodo y que tiene óxido de manganeso como cátodo puede durar del orden de 10.000 ciclos y son buenísimas para almacenar energía. Oh, sorry, I was hablando en castellano. I'm sorry. I will switch to Spanish because Portuguese is not. I mean, the question was about how long these batteries endure. The point is, ordinary lithium-ion batteries, that is the one you have in your telephones, may last hundreds of cycles. Let's say up to 1,000 cycles. But there are some materials which lithium titanate as anode and lithium manganese oxide as cathode, which may endure thousands of cycles, several thousand of cycles. These materials, lithium titanate, is not that good from the viewpoint of energy density because the battery is relatively heavy. But if you want to store energy in a bus, which is large, or you want to store energy in your house where you have no problem of weight, this battery is very good to make us thousands of cycles. If you are in a place, for instance, where you have only wind or you have sun, and you don't have access to the grid, and you have one of this battery, you may run this battery for years. 4 years. Very, very good. Some of them, they are very good. But the only point, I mean, the main limitation and the reason that people is working today so hard, people want to have the car of, let's say, 600, 800 kilometers. And this is no longer possible with the battery we have now. With the battery we have now, we can run a car with 200 kilos, which is a reasonable weight, 160 kilometers, not much more than that. But for many people, to be able to drive 50 kilometers, 100 kilometers is fine. That's it. For many applications, the lithium-ion batteries may be used today. And that's why there is to the people who analyze on the economy of that, they say that in 2026, what I read today, they are going, the battery car, the electric car, will be the same, will have the same price as ordinary cars, emission cars. So, I mean, there is going to be a big change in the economy of the world. There is going to be a huge change. I don't know if as a professor, yes, COMSOL is, I mean, what I showed today was all homemade programs. I mean, Kinetic Monte Carlo was homemade programs, and the other program that we used to simulations were all made by ourselves. But COMSOL is also a very good option for many users. COMSOL is okay. I have nothing against COMSOL, but we use some, for instance, in the case of Kinetic Monte Carlo, you don't have commercial programs that can do that. For molecular dynamics, I would say LAMPS. LAMPS is a very good option for molecular dynamics. So for DFT, density functional theory, you can use Quantum Espresso, which is a very good program. Siesta is also a very good program, and both programs are free. You can have them for free. LAMPS for molecular dynamics is also free. And Kinetic Monte Carlo, I don't know from commercial program, but you want commercial Monte Carlo, the Kinetic Monte Carlo, you can speak with us and we can do the best to lend you our program.
Mais perguntas, gente? Professores?
Roberto, eu tenho... Ezequiel?
Sim.
Posso falar em português ou em inglês?
Si quiera, en inglés quizás sea más fácil para mí, soy un poco duro de oído, pero...
Okay. I think it's the slide 115. You show voltammograms. 2 voltammograms for planar diffusion and spherical diffusion. But yeah. I work with microelectrodes. For microelectrodes, you have steady state voltammograms when you have spherical diffusion.
Yeah.
Your thermogram was not steady state. Why? Why not? I didn't understand very well.
I mean, well,
I think it's like.
It depends on the sweep rate.
Oh, okay. Oh, that's the problem.
We were using a very high sweep rate.
Okay.
The idea of this the idea of these plots, you define. This is something we devote some time. It was very fast because I mean, this was the final part. But this is a paper from Naoki a long time ago, and they consider diffusion in finite system, and they define these two parameters. Are you watching my screen?
Mm-hmm. Yep.
They consider these two parameters. This lambda tells you, depending on the rate.
Okay.
This is if you have a small v, you have a big lambda. That means you have a reversible behavior. No?
Okay.
And this parameter measures you the reversibility. That's why they make this plot. They make this diagram plots. When they plot this lambda and they plot this, and they classify depending. They make regions, and they analyze the behavior, the different limits, and they divide this, and depending on the rate and depending on the diffusion length, you will have different behavior.
Okay.
The voltameters I have been showing here are probably too fast. This is 1 volt per second. No?
That's you are going to have a planar diffusion. Okay.
This is a very fast, a very large sweep rate. But I only want to make the difference between this spherical diffusion and this planar diffusion, which they look very different, no?
Okay.
And
but
these are very huge. These are huge, very large sweep rate. But we wanted to use the same sweep rate that these people use in the article. No, this is a typical 1 volt per second. You can see.
Okay, that's fine. Thank you very much. Thank you for your presentation.
Thank you. Gracias a ti. Muchas gracias a usted.
Professor, first, I would like to thank you for sharing with us your interesting results. My question is about the intercalation compounds.
Yes.
So I would like to know which kind of two-dimensional materials have you simulated as a cathode for lithium battery? Yes, you have simulated graphite.
Yes, graphite.
Have you simulated other kind of two-dimensional materials?
I know what you mean. No, not yet.
Not yet.
Not yet. All we have simulated is graphite. We were, I remember that's why I thank Mr. Carlo for in the presentation, because when I saw for the first time the result of Auerbach showing these nice voltammograms, I would say I wanted to simulate this. So and we simulate the graphite, and we learned a lot, because the interesting thing we learned two interesting things from graphite. One was that this partial molar entropy is this order-disorder transition, no? Because you you fill one layer every 2, so you have an entropy decrease, and we are finishing to fill one layer. You get a sudden entropy increase because you start to fill an empty layer. This was for us a surprise. And you know that this order-disorder transition were very well known for cathodes, but they were not known for graphite. So we discovered that in the case of graphite, this step in the entropy was an order-disorder transition, which was not that far. So after we did that, and after we went to read the cathode, we said, okay, this is very clear. But as long as we didn't, nobody has thought on that for graphite. No, that was for us. We were very happy to find that.
Okay.
And the other point interesting in graphite is this problem of this defective structure, no? That you get instead of filling one layer, actually, if you look at the energy, this defective structure have a high energy. But the point is, you start putting lithium inside. At a certain point, you get to an occupation where the most stable phase would be 1 every 2, but you have all layers filled. So the only thing that the system can do to lower the energy is to make all these defects. And you cannot, if you make a simulation where you artificially increase the exchange rate with the solution, that the system can minimize the energy, you finally arrive to the perfect structures. But this is out of the possibility to make an experimental system because the change current density because it's too low to get this equilibrium structure.
Okay. Thank you very much.
You're welcome. Thank you.
More
Roberto.
questions? Ezequiel, I have many, but I am choosing someone. For example, in the case of silicon, that you can understand very well and with the model, see what happens with all the mechanical change during the intercalation. It's not really an intercalation, but the formation of the alloy with lithium. So can you make also a modulation taking into account the nature of the electrolyte? Because there are some experimental results that, you know, the lithium using silicon as anode, when you change the electrolyte, it is better for the life of the electrode. So it sometimes this is related with the nature of the electrolyte. So you can build a model that you can play around with the nature of the electrolyte?
Oh, I don't know, but this is a very interesting point. If you have some idea what is the electrolyte making, you know, this is not, you know, although this is reactive force potential, this is not quantum mechanics. So it's very difficult to put some chemistry there. But if you have some idea what is the electrolyte doing to the surface atoms, you could try to put some interaction potential there to simulate what the electrolyte is doing and try to know what's that. But what we cannot do is to study, for instance, the decomposition of the solid, the SEI. We can't do that, no, because you have chemistry there. Now you know that when you know that when you start to lithiate, there's also some decomposition of the electrolyte, and this changed everything. So I don't know. I mean, if the electrolyte is doing something very, very simple, we could simulate that. Otherwise, you have to look into quantum mechanics, to see what's going on, and try to put them back into the simple model. Because I mean, this is the idea of this. At the end, I mentioned this multi-scale model, and the idea of the multi-scale model is to go up, you know, to quantum mechanics, go to other model, to improve, to go back and see, because it's impossible to simulate with quantum mechanics the limitation of a big structure, you know. So the answer is, if the solid is making something simple, we could try to put it from outside, let's say. If the solid is making some heavy chemical reaction, I don't think we can do it with this tool. But it's something with this would be interesting to analyze, of course.
Well, I have another question. It's related with the voltammogram that you made with the kinetic, Monte Carlo kinetic.
Yes.
I didn't get, this is a voltammogram for intercalation material, or it's a voltammogram, you know, for
an intercalation material. Yeah, I was too fast, but I can go back a while. Yes, you know, it's the same what we do is the simulation that we do. I go back to that.
You are not showing the.
Oh, I'm sorry. I show my screen. Yeah. I mean, the voltammetric simulation is the same as the simulation as the potential step. Wait a minute. I want to go back. I'm looking for the slide. Just give me 1 second. I explain you how we make the simulation, so you will get it at the moment. So as I told you, in this simulation, we allow, every time step, we try to say, okay, the atoms may move, the atoms may intercalate, the atoms may intercalate. This is for a potential static step, we put a potential constant. If you change the potential, every time step, we change also the potential here, and you get the rates of the insertion, the insertion will be changing with the time, and you get a change of the occupation of the system with the time. So this is the voltameter insertion, the insertion voltameter. So when you go to that, this is the peak. If you run faster and faster, these peaks merge together, but you go slower and slower, you get the peak for phase 2, and you get the peak for phase 1 for the formation and the dissolvation. So this is a voltameter for the formation of phase 1 and phase 2, and this is what we get from the model. Yes.
No, perfect. And the last question.
Roberto, see that you can show here, no? You can see here. This was 10 milligrams.
Yeah.
You have hysteresis, 5 milligrams, 1 milligram, and you make 1.15. You get practically no hysteresis. So you get the rest. This is the nice thing of kinetic Monte Carlo, that you really get an answer depending on the time.
Someone want to make it? No. Okay, the last question that I have is, how did you choose graphene to study with sulfur?
No, it's a model system, no?
Okay.
It's a model system. Graphene is a reference. That people, graphene is just a reference. Let's say the interaction of graphene with sulfur is not very good, but it's like a reference, because it's, graphene is very easy to put in DFT. Otherwise, you may say, okay, you don't really have graphene, you have some other sort of carbon. I need to put some structure to make the calculations. And the most simple thing we have to put is graphene.
Okay.
If you know how you can tell me, no, okay, I know from this carbon and I know how this carbon is made. Okay, we can put this carbon into the model and you can give you an answer. That's why the answer is really the most simple thing we could find, and graphene is the most simple thing we have.
Okay. So someone has some question to. No.
Roberto, can I ask a last question?
Yeah, of course.
As you are an expert in batteries, do you see a future for sodium batteries to replace lithium batteries?
For me,
in the future,
I don't want to. I do not want to.
I know.
Because we have lithium. No, there are two things. Sodium battery is heavier, no? The reason Europe is investigating making research on sodium battery, they do not want to depend on lithium, because lithium is concentrated in a few places of the world.
That's a problem.
Sodium is there are two things. Sodium is heavier, so the capacity of the sodium will never be that of lithium. So I don't think, but for practical applications, sodium will replace lithium. But there are some other, there are some other materials like magnesium or aluminum that people is making research with. The problem of this, for instance, for aluminum or magnesium, is that the ions have a charge of 2, and the diffusion is a big problem, because if you have a single charge ion, because the diffusion is faster, much faster for a single ion charge than for a double ion charge. And that's one of the problems of ions with higher charge, because lithium is some sort of magic, because when you start loading graphite, it's like a miracle why the graphite works, because when you start to deposit, you get a formation, the composition of the solvent. But magically, this solvent makes a layer, and this layer is ionic conducting and electronic insulating. And that's why the ions diffuse very fast and come in and come out very, very fast. But if you have an ion with a charge of 2 or an ion with a charge of 3, the diffusion across this layer is much slower. So in the ions with a large charge, we have a very problem about rate. No?
Okay.
What can I answer as far as I know?
Okay, thank you very much.
No, you're welcome. So
More questions?
I encourage in Brazil to work on batteries. You know, you have, as I told you at the beginning, you have all the material, many of the materials that you need with the raw materials of the batteries. You have all these materials. You have graphite, you have manganese, you have a number of things. Well, together with the Paraguay have titanium, Chile has copper. I mean, in the region, you have all the materials you need to make the battery are here. We only need the technology, but the only is the most.
Ezequiel, you have a question in the chat.
Sí.
Leandro, the other professor of the...
Okay. I'd like to know what is best of company to simulate the product lithium massive battery integration on a carbon component, and I'd like to hear something about this study and specific layer of size sandwich. Well, I mean, this is something where I mean, if you have some idea, you know, in the kinetic Monte Carlo problem, you need basically a lattice. So if you have some idea how the lattice is made or how is the size of distribution, you can make kinetic Monte Carlo. You can estimate rates and you can do that. I mean, you could simulate a morphocarbon. You can also simulate other interstratified material. This is something we are thinking to do. We in the next time we want to simulate other stratified material with kinetic Monte Carlo. I think it's very useful. It's something. The thing you have to study or to have some idea which are the activation energy for the motion of the ion. If you have some idea of the activation energies, you can do it. The other thing is the other thing you can do is to there are too many things you need to make a calculation. One is the diffusion of the ions inside the material, and this is something you can fit if you have the diffusion coefficient. You can fit that, and if you have the exchange current density, if you have the exchange current density, you can fit the other parameter and you can run simulation with that. This is something that can be done. So you need to measure. It's good to have measured the diffusion coefficient and the exchange current density. With these two parameters, you can make the simulations. And some fitting, of course.
So this question comes from the YouTube.
Okay, gracias.
Was Alfredo Duarte, that is a student of Vera Constantino, that did the question. Another one.
Well, as I told you, I mean, about sodium, I told you before, I mean, sodium has this problem that there are not as many materials. One of the problems with sodium is you cannot put sodium into graphite. No? Sodium can't get into graphite. I mean, this magic. Lithium comes into graphite because the other thing you have to consider is the potential, no? Because you have to decrease, when you load the battery, you have to decrease the potential more negative, and sodium doesn't get into graphite. For sodium, you have to use to the other type of carbons, no? So your graphite is out of question. And you have a lot of graphite in Brazil, so graphite is good for lithium. And concerning electrolyte, well, I mean, the question of recycling. Recycling is a very important topic, and I think it should be worked more on recycling because we will deal with a huge amount of battery in the future, and the question is what will we do with all this battery going around, no? And I must tell you, most of the battery we have now, all the battery we have here in our pocket, have a cobalt. Cobalt is here. Cobalt is very expensive, and cobalt is poisoning. And in spite of that, we are throwing the batteries away. This is one of the things that to come. That's why people are trying to get rid of cobalt. Sodium, I think, is interesting. Sodium is more abundant than lithium. That is one of the reasons. Sodium is everywhere. But has its inconvenience, is heavier, and I think that there are not as many materials with sodium as with lithium. But okay, it may happen in the future. But again, I think concerning cars, I think lithium will be, at the moment, the best choice. And the next generation of battery is probably lithium sulfur, but lithium sulfur had all these problems we're speaking about. This is one of the problems, this motion of this polysulfide shuttle. And the other problem with the sulfur is that you use a nano, which is made of pure lithium. And pure lithium is maybe a problem because pure lithium, you know that pure lithium is very reactive. And the other problem is security. There are many issues in battery. One is security, and with lithium is a security issue dangerous. No, with lithium is very reactive. You make a hole in the battery and it's over. No, so this is one thing that must be solved in the future. I hope I answered the question.
More questions? Okay, so I think that we can close our day.